In this video, we're going to work backwards a little bit. And what I mean by that is, normally, what would happen is we'd be given an equation that looks like y equals a sine of b x take h plus k, or a cos b x take h plus k, well, something like this. And we would be using our knowledge of what these a, b, h, and k values are in order to sketch. Now, we're actually just going to do the exact opposite of that. We've got these positions here on this graph, and we're going to use our knowledge of trig functions to work our way backwards. So, I'm obviously going to start with whatever is the absolute easiest for me to see, which is usually my a value. Now, the a, we're going to be looking at this equation here, okay, because it's a cosine function. So this a that we're going to be looking at is my amplitude, and my amplitude is essentially how much it is stretched compared to normal, and the amplitude is half the distance from the maximum to the minimum of the wave vertically. So we'll do that in yellow here. I am going from 4 to -8. So that is a total vertical distance of 4 plus 8 equals 12 vertical units. So that's not my amplitude though. My amplitude is half that. So in this case, my amplitude is half that. So my amplitude is 6. Now, let's also continue to think about this a value, and I'm going to think about what a normal base cos function is. I'll quickly sketch that up on the right. A normal base cos function, okay, if I was looking at a y equals cos of x, it's going to start at 1, go down, and back up. So what we're going to have is we would have started at 1. We'd be starting at a maximum. Now, if we have a look at this graph over here, our graph that we're looking at here has been flipped upside down. It's been flipped across the x-axis. So that means that my a is negative because reflected. Okay, therefore a equals -6. I might actually move this working a little bit so it sort of sits down here. So therefore our a is -6. So we've ticked that one off. All good. Now let's think about our equilibrium position. Normally, our equilibrium position, and we'll do this one now in green, my equilibrium position normally sits across here, across the x-axis, and we simply go from a +1 down to a pi and -1 at our minimum. So our amplitude of 1 normally has an equilibrium at y equals 0. That's my equilibrium. Now, where's the equilibrium on our graph? Well, let's have a look. Let me get rid of some of this stuff here. Okay, on our graph that we've got over here to the left, we go from 4 down to -8, and we just said our amplitude is 6, and amplitude is half the distance from the maximum to the minimum, which means if I was to look from this 4 to this -8, the point that is halfway through is here at y equals -2. So if it's at -2 all the way up to 4 is 6 units, -2 all the way down to 8 is also 6 units. So perfect, I've got my equilibrium position. But what number does that affect? Well, the equilibrium position is going to be affecting our k value. So k would, if there was no value of k, if k was 0, then my equilibrium position would still be right across here at y equals 0, but now it's 2 units lower. So I'm going to write equilibrium at y equals -2. Therefore, k equals -2. Okay, we're just slowly using this information that we have about this graph to work our way backwards. All right. Now we have to think, is my graph slid or shifted or anything else that's going on here? So let's now rub out some of this stuff that we just drew. Okay, so we can look back at our graph now. We've used our knowledge to get A and K. We did our verticals first. They're usually the ones we do first. Let's now have a look for H. Well, we're starting here. Our maximum on a base function, as we always do, look at the base model, is our maximum is the very first starting point. Okay, well, we already know it's been reflected if we look down here, so that means our minimum should be the very first starting point. It is. If we have a look at this, our minimum is the very first starting point. So what I'm going to say is no shift left/right, therefore H is 0. H hasn't, there is no H. H hasn't done anything. Okay, our A is the thing that's moved away from being a maximum, so now it's a minimum, but it has not been slid to the left or the right. Okay, we're not starting on some sort of random point along our wave, like we're not starting at here, for example. Okay, we're still starting at a major key point, so that means our H hasn't slid our graph anywhere. Lastly, we're going to look at B. Now B is all about period, so period. Now normally, again, on a wave, we'd go from 0 up here, pi down here, and then we'd finish up here at 2 pi and 1. Okay, so our wave would finish up there at 2 pi, and half of our wave was here at pi. Well, let's look at the period of this wave. Well, our halfway point on a base wave is pi, and in this case, our halfway point is pi on 3. So period of this wave is 2 times pi on 3. So 2 pi on 3. Now, how does B affect our period? Well, normal is 2 pi, but if we divide 2 pi by B, then we end up getting this period. So all we have to do now is rearrange this to get B. So what I'm going to do is I'm going to bring this 3 up here by multiplying. So what I'm going to get is 3 times, oops, go again, 3 times 2 pi over B equals 2 pi. Then I'm going to bring this 2 pi underneath and divide it. 3 times 2 pi over B times 2 pi, brought that 2 pi underneath, equals 1. And then I'm going to get these 2 pi's cancel out. I'm going to have to bring this B up and multiply it. And what we're going to see is B equals 3. That was a pretty long-winded way of looking at it. What we could have simply done is looked at this section here and simply thought logically, if 2 pi divided by B is the same as 2 pi divided by 3, we could have just come straight from there and said, well, therefore B must be equal to 3. Now, what we've done is we've used all the different features of this wave, the amplitude to get our A, the fact that it's mirror imaged to get the negative or positive value on the A. We've used our equilibrium point to get our K. We've used where the maximum sits to get our H. And then we've used the period of our wave to get our B. So all we'd have to do is final function is equal to, and we're just going to put all of these numbers up here into this wave. So final function y equals -6 cos cos of 3 x take 0 take 2, but of course we don't need to write this middle bit the way we did. We can of course tidy that up to be cos of 3x take 2.